All right, so this is 127, exploit development, and we're down to Windows. And I updated the first 4 Windows projects, and we'll go through the theory of Windows exploits, and then through the first main Windows project. And remember, I told you at the beginning of the class that the most important project in the entire class is this one, ED202, where you learn the basics of a buffer overflow on Linux. And the second most important one is this one here, ED308. That is where you do the basic exploit on Windows. This is the most important thing, to really understand how to exploit a buffer overflow on Linux and how to exploit a buffer overflow on Windows. And everything else in the course is just minor variations on those 2 projects. So those are the ones to make sure you understand if you want to go on and get certifications. The certifications that match this course are OSCP and probably even more exactly OSED. Anyway, not that these courses prepare you entirely for those certifications. They're very difficult, but they move you some distance towards it. So let's take a look at the slides, which are here. All right. And this is the important stuff, understanding Windows. Windows is extremely important and extremely complex. It's far more complex, in my opinion, than Linux. Those certifications are OSCP and OSCE. Here, let me put a link in if you don't know about them. If you want to get a certification in the stuff here, OSCP is the main certification you get if you want to be a pen tester. This shows you that you know how to attack servers and take them over using normal attack tools, which is what our pen testing classes prepare you for, 123 and 124. This is the most popular certification for working penetration testers. And the one particularly related to this class is probably, I've been told by students who got it, I don't have it myself, is OSED, which is the exploit development certification. And there's also something called the reverse engineering certification. So I'm not sure. I think there's also a reverse engineering one from the same group. This offensive security is the people that make Kali Linux. And they are considered the best certification for hardcore technical security people, outside of, say, SAN certificates, which are extremely valuable, but they're very expensive. These are those are certificates that you might want to try getting, although I'll warn you, if you take all the courses we offer at City College, you're still not ready to pass either of those tests. You have to take all these courses, and then you have to do a lot of extra study beyond that. They are quite advanced. They are not multiple choice tests. They put you in, they connect you to several servers, and you have like 36 hours to hack into those servers. And then you have to write a report documenting how you hacked in. That's it. It's real attack. So that's why it's so highly valued. Yeah, but check those out if you want to get a job in this stuff. Those are very good certificates to get. Everybody values the real hands-on certificates much more than the multiple choice certificates. This is another reason why people value Cisco certificates so much, because the courses have hands-on finals. All right, good. Anyway, so here's what we're going to talk about Windows, the basics of how Windows works, which if you took 126 last semester, malware analysis, you'll have already seen all this from the defense side. 127 is basically the same content from the offense side. The basic structure of how the Windows operating system operates, and the memory structures, which are particularly important to us because the exploits we're doing are the most common kind of exploits, which are memory corruption exploits, where you manage to put invalid data in memory regions. So the heap, threads, DCOM, exception handling, and debuggers are topics you need here. So the API is the application programming interface. And wait, I have, regarding Velociraptor, I see a question here, putting the IP address on Windows clients, but I couldn't get it through and prompt remote dial. All right, I'm not sure about that, but if you come back at 7:30, then you can share it on Zoom, and I'll try to debug it. That's probably what I have to do for that Velociraptor question. It's a good question, though, and I'm happy to help people get Velociraptor working, but after the lecture. All right, so the API is what Windows provides so you can use it. And the same thing's true, by the way, Facebook and any other operating system or platform. It is an application program interface lets you make requests to the operating system to do something, and then it will do it. And this is what basically limits what you can do. You can only use Windows to do what the developers intended for you to do by providing API calls. Now in Linux, you use syscalls to talk to the kernel, but in Windows, you use the Windows API to do it, where you send some structured data and call one of the Windows API functions, and it's implemented as a set of library calls, DLLs, which is dynamic link libraries, and they change it frequently. So you have to use dynamic linking to get to the DLLs, which means that your program will request a connection to a named library, and the operating system will decide if that library is already in memory. If it is, it will connect you to the image of that library that has already been loaded for a different program. So you will both share the same image. This makes your program load faster and consume less memory, but it's also dangerous and unsanitary because two programs are using the same library, and it is possible to trick a program into connecting to the wrong library. But that's the technique that's used in Windows because speed and efficiency is valued over security. All right, so here's an API call. For example, if you have a program and you want to open a window, you can call create window EX, and then you have various parameters here, including the title of the window and other things down here, like whether it will have a scroll bar and how big it is and so on. And the end result is you get a handle to your window, which you will now refer to with other calls, for example, to close the window or move it around or something. So the DLLs are precompiled library code. You load them when you need them. It automatically will be loaded when you run the executable, and you can see them with Process Explorer. Process Explorer is just a souped-up version of Windows Task Manager. It's a free from Microsoft. It's not built into Windows by default, but you can download it. And then if you look at a process up here, you can...
Sorry, could you say that again?
This
I couldn't hear what you said.
Stupid, worthless Apple junk is listening to me again. I've never found any way to turn off the stupid voice sensitivity of these Apple devices. I tried a few blogs and none of them will turn off. Anyway, so every time I buy an Apple device, I spend the next week or two trying to turn off 90% of the features. Most of them are just garbage, but I like some of them. Anyway, so these are all the libraries used by this process, and you can see them in the running process there. Now, portable executable files are the files for all executables on Windows. It is the general category called portable executable, and that includes EXEs and DLLs and COM files. And so they can be loaded on any version of Windows, and you can see the structure of a portable executable file with the free tool PE View. So here's Notepad, and it's got a header. It's got headers, and it's got various sections here. You see it has text, data, resource, and relocation sections. These go all the way back. In fact, I just saw recently they go all the way back to the PDP-11, the first mini computer from, I think, the 70s. So these are really old concepts. Anyway, basic sections of a file, and then you have an import directory. Here's where it tells it all the libraries you're going to use. And so it needs to load this advanced API 32 and kernel 32 and GDI 32 for graphics and so on. In the header of every executable is a list of all the libraries it needs to load, and when you launch it, it uses that list to connect to all the libraries in memory. So here's the sections you'll see in a PE file. You can have a variety of different sections, but you always have to have a text section because it has to have some instructions to execute. And the general rule for everything in Windows to remember things is everything is always named the opposite of what it is. Not because Microsoft is stupid, but because it dates from a long time ago. These names have changed their meaning many times over the decades. So the text section is not readable text, it is machine language instructions to execute. The readable text would be in something like the resource section. So then you have variables in data and iData, and then data that import descriptors, resources like icons, and relocation data, which is used to relocate this program in memory, if necessary. So that's relocation. Your library has a natural base address, and if you load it at the expected address, it will load quickly and not have to make any adjustments. But if two DLLs try to load at the same base address, they can't, so one of them must be relocated, and that's why you have that relocation section, which lists all the corrections that must be made when loading it into memory if it's loaded at some other location, which is called rebased. How could you DILs have the same base address? Oh, well, you have to put something in there. And I think it's because the PE format dates from long ago before there was any address space layout randomization. You would just tell it what memory to put it in. And so Microsoft DILs tend to choose different addresses to avoid this, but third-party DILs might all just have the same base address. And you won't really notice. It just means that you have to go through relocation when they get loaded, but technically it's a little less efficient. Well, they do load, but it will notice that something's already using that address, and it will move to another address. And then it'll use the information in the relocation section to adjust the hard-coded addresses inside the library. All right, see, good questions going by. All right, let's take a look at a Kahoot. 6A. Kahoot, have I tried? I have not tested the trans thing yet. I don't want to get my Kahoot account canceled, but there is a news article saying that if you put any questions, including the word trans, your account will be frozen because it is considered a violation of the law in Utah and Texas to refer to the word trans, which might refer to transsexuals and therefore offend the fundamentalists in Utah and Texas. But you're right. I don't know if that's true. I didn't test it. By the way, I wouldn't get hurt anyway because all my Kahoots are private. Yeah, transgender. That's transgender or trans, something like that. If these things violate the laws that have passed in those states recently. The Don't Say Gay bill, I think is what the people that hate it call it. I don't know what the official name is. That's not the official name. But anyway, Kahoot has implemented it rather sloppily by just blocking anybody that uses the word trans. There's the problem with bills like that block certain words or something. Then when you implement them, you tend to have collateral damage. That's why most people hate things like the gag order. Legislators frequently forbid you to talk about things. The gag order I know is the anti-abortion gag order, which is particularly heinous. It means your doctor cannot talk to you about certain topics. And that seems like a really bad idea. Your doctor and your lawyer should be able to tell you anything. They're people that typically have to talk to you when you're in trouble and you need to hear something ugly. So you really need to let them talk. Anyway. All right, I guess we've got everybody. I'll give it another few seconds. When I grew up, that was the rule. You can tell your doctor and your lawyer anything, and they won't rat you out, because you need to tell them dirty secrets, and they need to help you deal with it. Anyway. All right, where is the precompiled library code? All right, those are the libraries, dynamic link libraries. All right, the functions Microsoft provides for software to access the kernel. The API, all right. All right, so what is the format for all Windows executables? All right, they're PEs. They're not all EXEs. DILs are also executables, and so are COM files. The container for them all is the portable executable file. All right, what part of a PE file does rebasing? All right, relocation. All right. All right, where are the machine language instructions in the PE file? In the text section. All right. And where are the icons? All right, they're in the resource section. Good. All right. So, all right. I think I know who that is. And that, good. All right. Good. All right. So, imports are functions that you use from other code. So if you have an exe and it uses a library function, that's an import. If you have a library, it typically also uses library functions, so one library depends on another. Exports are pointers you export so that people can enter your program at that point. Now, an exe typically only has one export, which is the main or start routine, where it starts and you're not supposed to enter at any other point. But a library has many entry points for the various different functions. So DILs have a lot of exports. EXEs typically have only one. All right. You can see them in PE view. So here's Notepad. Here are the import table. And you see it loads from advanced API 32.dil, and here's the actual specific functions it uses from there is text Unicode and event unregister and event register and so on. And then it loads from comctl32, just this one function, and so on. This is in the, again, in the headers of the API. It tells it exactly what functions you're going to connect to in what library. Those are the imports. And here's the exports from Advanced API DIL32, seen in PE view. And as you can see, there are a ton of them. These are just the A's, and I only get down to AD, and the scroll bar is here. So hundreds of functions are included in this library for the Advanced API. So the Microsoft API is huge. There are thousands of API functions across many libraries that you can use. And the Microsoft documentation is extensive, listing all of them and what you can do with them. And there are a bunch of them that are undocumented. And people have just figured them out, or it's leaked from inside Microsoft, ones that were really only intended for internal use. All right, so when you launch an exe, Windows tries to find all the libraries and load them. And these days I don't see this so much, but back in the days of Windows 98 and Windows XP, it was very common that you would get error boxes like this saying it can't find one of the libraries, and this put you in the world of DIL hell, where you're hunting around trying to find the DILs. Exports are functions that others can use. Imports are used by the program specifically. Yes, that's right. Exports are functions you're offering to others. Imports are the functions you are using from somebody else's program, typically libraries. Exactly. So when you launch a program, it'll try looking in the current working directory, and then it will go hunting for the DIL. And you can often trick it. This is how the Stuxnet attack works. You can trick it into loading a DIL that is not the genuine DIL, that's loaded in a different directory. That's called a companion Trojan, and it's a very common one. And so the Stuxnet that we used to attack the Iranian isotope separators had you put in a floppy disk, and it would have a DIL right on the floppy disk, which was loaded right away. And this had malicious code, which took over the machine as soon as it drew this box. You didn't have to launch the program or anything. It took over the process that displayed the contents of a floppy, which was very clever. All right, so Windows executables all want to load at 400,000. I've never seen one that has a different base address. That turns out to be a virtual address. They all think they are running at 400,000, but they're really loaded somewhere else. So the EXEs have a virtual address they use, but their actual address is different for each one, of course, because two of them can't use the same physical memory. So, for example, you might load this program might load at 300,000 and this one at 500,000 in physical memory, but they both internally think they're loaded at 400,000. That's their relative address. So here's OllyDebug, one of the debuggers we use. And so when you load a program, you see the code starts near 400,000. This is a code that loads at its default location. You'll see the machine language instructions beginning at 401,000 and so on. All right, so now the heaps. The heap is a place you temporarily store data that is not ordered, like last in, first out, like the stack. It's just a place where you can put lumps of data of any size and delete them to make room for more data. So a lot of temporary storage is there. You allocate space with malloc and you free it with free. Linux uses one heap, but Windows uses many heaps. And there are a lot of fancy features on Windows heaps to try to make them more efficient and decrease fragmentation and stuff. They're really quite complicated. So heap corruption attacks on Windows get pretty confusing. All right, and then threads. This is a big issue. DOS was a single processing machine. You only run one program at a time. I remember in the days of DOS, if you wanted to add a graphic into a document, you would have to stop the word processor, run the graphic program, and then somehow merge the files. And if you started it printing, you'd go get a cup of coffee because you couldn't do anything else until the printing stopped. It could only be doing one thing at a time. But Windows can be doing multiple things at the same time. Many processes can run, and each process is further subdivided into threads, and each thread can move forward independently. So if one thread halts waiting for something, like for example it's popping up a box asking the user to click yes or no, that thread can't move until you answer that question, but other threads can keep moving while that thread is waiting. Better for mental health to have single processor machines. Well, that's true, yes. Anyway, so the processor gives a few cycles to this thread, a few cycles to that thread, a few cycles to that thread. Every thread gets its chance to move. So some part of the programs, the many programs you've launched, some part of them will keep moving, even though some of them are always waiting for something that's slow. That's the idea. You can see them in Task Manager. You can go here and it will show you this machine is 3% of the CPU is in use. There are 41 processes with 677 threads and 18,000 handles. Yes, scheduler, I think that's right. Task Scheduler is what does this. Yeah. Well, the Task Scheduler I know is for scheduled tasks, which is just things that trigger at a certain date in Windows, the thing called Task Scheduler. But I think there is something doing this threading, and I'm not sure that's the right technical term for it. As thread instructions are being executed, it becomes process agnostic. No, each thread is contained in a process, and it stays attached to that process. So, for example, if you close the process, all those threads will stop. Now, threads are contained in the processes. They're not independent, but they each get their chance to move as the processor gives each thread an opportunity to have a few cycles, and then the next one, and then the next one. So handles, you notice there are many, many handles here. The handles are pointers to things. Remember back up here when we had an API call to open a window, way back here, there. This is the handle, HWND. When you create an object in memory of some kind, you get a handle to it, and that's just a way to refer to it later. So if I want to close a window, I need to tell it which window to close, and that handle is how I refer to it. So each thread will have many handles. These are pointers to files and other objects that you're using. All right. So that's the game, and you can view the details about every thread in Process Explorer. You can go to a process, like down here I went to Explorer.exe, the process that draws the desktop and the start button, and then went to the properties of it, and you can see the threads with the thread ID, all the threads in here You can get information about each thread. This is something you would normally never look at unless you're trying to debug something really nasty. But anyway, you can see every detail of every process, enough to drive you nuts. All right, let's try some more Cahoots. All right. All right, give it a few more seconds. Aha, okay. Better give it a few more. All right, let's go. All right, so what part of a DIL lists the entry points? Yep, that is exports, not imports. Exports are handles you export locations so people can enter here, or you can enter there, or you can enter there, because I'm a library and I offer several functions. It's easy to get them backwards, but anyway, that's the way it works. Exports are entry points you are offering to other processes. All right, which memory section is a single block in Linux, but many pieces in Windows? All right, there's a heap. That's it. All right, which item has the largest number of instances? All right, handles. You have a certain number of windows. You have more processes because some processes don't have windows. Each process has many threads, and each thread has many handles. This is the most numerous thing. All right, what's the allocation unit for CPU time? All right, and that's the thread. Each thread gets a chance to move forward, and the processor strobes through the available threads. All right. All right, TV's a 2-time winner. And JC, you'll have to tell me who they are. There are, in fact, 3 JCs. All right. And someone says, is a NOP to balance out the timing of the threads? It's Jordan. Okay, good. Okay, good. All right. No, the NOP does not balance out the timing of the threads. The only point of a NOP is to fill in gaps between instructions, because some instructions have to start on a 4-byte boundary. So you can have a small instruction, and then you have 2 or 3 bytes you have to skip over to get to the next boundary for the next instruction. That's what NOPs are for. Good. These are good questions. So now we can talk about DCOM. And this is the, like I say, the genius and the idiocy. This is where you have to understand the purpose of Windows. Now, Bill Gates, when he was 17, went to the computer users groups where everybody would just get together and try to build computers and try to write programs. And he wrote a basic interpreter. And the first thing he did at the age of 17 was circulate an angry letter saying, people are using my code without paying for it. You are a bunch of pirates, which they were. Right from the very beginning, Bill Gates was a businessman. He wanted to make sure he was making money for his software. Microsoft is a capitalist business. The whole purpose of it is so Microsoft can make money, and so all these other people can make money by writing programs on Windows and selling them for money. So it's designed for that. And this is a structure designed to make it more efficient for people to buy and sell software on the Windows platform. So you have the distributed common object model and the remote procedure calls. So the point of this is you can build an application without writing all the code you need. You can pay other people, and you can buy code that they've already written and license it to put it in your application. That's the idea. It is designed to let you make your program not by writing all the code from scratch, but by buying pieces and stitching them together like Frankenstein's monster. That's the idea. So, COM objects can be written in any language, and they can interoperate with other COM objects and with Visual Basic Code. So you can just write a sort of top-level calling program that calls somebody's code to do the login, and calls somebody's code to do the crypto, and calls somebody's code to do this and that, and patches together to build your app. So the problem is you're catching together modules that were written in different languages. And that means the actual data structures are not the same. A C++ integer is not the same thing as a Visual Basic integer. So you have to have an object to explain what kind of data is being sent from one object to the other, and that's what an interface description language file is. It looks like this. You have these universal identifiers to identify what you're talking about, and then you have a structure, and down here you have a long integer, and a couple more long integers, a handle, and a few pointers. You have a data structure defined by this, which can be used to send data from any language into this code that was written in a different language. And the point is you can reuse code. So it specifies all this. So the original story, back in the old days of MS-DOS, I think, although I'm not absolutely sure they had it then, but I think they did, you can write code in a DIL, which then loads into your one process. So it's just going to be loaded and accessed by one process right on the same machine in the same memory. That was the original context in which code was written. But you can then decide to resell your code to be reused elsewhere by service. You load it as a service, and now it's offered to all the programs on that box. Then that makes it slower, but more stable. It's running in a more separate way than being attached inside one program's process space. So the Service Control Manager is called services.exe, and it's always running on Windows machines, and it runs a whole bunch of services, 40 or 50 of them or more, running in the background all the time. Now, DCOM calls make it possible for you to make a small change in code to say, I want to make this code available to other processes on this machine, or I even want to make this code available over the network to calls from other machines on the network. So build it into one process, it would be fast. It's 1,000 times slower to make it a service, and it's another 10 times slower to make it listen on the network, but you can run the same code. Is that SVC host you see in processes? Yes. Most services are launched by the SVC host exe. And if you use Process Explorer, you can see each SVC host is servicing 5 or 6 services. And that's why you'll see 10 instances of SVC host running. So, for example, the RPC endpoint mapper, this is remote procedure call. This is offering code over the network. So it listens on TCP 135, and this is famous because a ton of worms and other exploits attack it here, because this one port is used to serve many services, and as we're about to see, they are notoriously insecure. So you make if you look in Wireshark to watch the packets, some other machine tries to come in, does SYN/SYN/ACK on port 135, then it does a map request and gets a map response which says, what services are you offering for remote procedure calls on this machine? And it will then give you an answer which has these things called floors and gives you 5 options. There are 5 things running on this port that you can connect to with different UUIDs, the universal identifiers, these 128-bit numbers. So that's why so many worms attack this. This one TCP port is used to lead to a whole bunch of code running as services, offering service over the network, and that code is notoriously insecure and unsafe. Now you can see how this works in services. You can go into a service and you can see what it depends on. So RPC depends on DCOM, and here's the many things, all things that depend on RPC. So one service depends on another service, and that depends on another service. So you're actually using a lot of them every time you do something. And this is analogous to the problem with Python and other languages where you use libraries, and the libraries call other libraries. And now if you ask, like, what country was the code I'm using written in, you're using code from all over the place, far distant countries you don't even know about. Anyway, so you're using a lot of services all the time on Windows. Yes, it is like RPC bind under Linux, and there's a task list. Yeah. You got the command line to see it in Task Manager. All right, so now the reason why this is so insecure is somebody writes code decades ago to be run on one process in a trusted environment on one machine. Then somebody else later takes that code and says, oh, let's share that with all the applications by making it a service. And later they say, oh, let's share that with everything on the network by making it an RPC. So code is moved from a safe, sandboxed environment to an unsafe environment. And this is analogous to another security disaster we're all living through. People take their servers that are in their own locked server room, and then they just put them up in the cloud. So all this data is just on Amazon Cloud, and they don't really understand the consequences. And that's why there were so many open Amazon buckets where your database that used to be secure behind your firewall is now just available to the whole world because you put it in the cloud without knowing what you're doing. You took something designed for a limited secure environment and just put it in a broader environment. And if you do that, you have to rethink the security consequences, and people often don't, which is why so many of these RPCs are ridiculously insecure, because they're running code that dates from earlier decades when people didn't think about security, and from a trusted environment where security wasn't that much of a risk. And then you just take that code and export it to a wider environment. So there are a bunch of hacking tools to do this. Recon, fuzz, and exploit. You can do all these things with Spike is one of the many hacking tools for this. And there are others to do queries of the remote procedure calls and find out what they're running and try to find vulnerabilities in it. So that's the system that's being used by Windows. Now here's another system. When you run a process, you have to know who you are and what privileges you have. And that's done by a token. And you can see that in Process Explorer also. So here's Explorer.exe. This is the process that draws the desktop and the start button, and you can see it's running with Sam's token. This is the name of my Windows machine, Sam, and it's just a pointer to a data structure. So the token is just this number, and this token has to be attached to every process so it knows whether this process is running as administrator or the currently logged on user or system or network service or any of a variety of possible privilege levels it might be running at, users it would be running at, which determines its privileges. So you can create a thread and you can attach and copy somebody else's token to it if you have local administrator rights. And this means if you have local administrator rights, you can hunt through this list and see if somebody is running something as domain admin, which they often are, because they've let some kind of update process or something run. And so you can copy higher privileges onto a process and gain higher privileges that way. Why do some of these tokens have the same type and name but different object addresses? I don't think they do. The 3 E7s are both the same. Oh no, 30 and 40. That's a good question, and I do not know the answer. You're right, there's two kinds of 3 E7. I don't know. I would suspect it's because the name is not precise. You can also have accounts where you can't resolve the name. I would guess it's some kind of error in resolving the name, but knowing Microsoft, there's probably a complicated reason. There are many complications in these service accounts on Windows. All right, good questions. All right, so then we can talk about exceptions. Bad things can happen where a process tries to execute an instruction that's illegal. For example, it's trying to execute an instruction that is a kernel instruction, but that process is not running in the kernel, or it's trying to execute an administrator process it's not allowed to, or it's trying to access a memory region that is not available to that process, or divide by 0. All these things are exceptions when something illegal happens. So something has to happen, and what you do is you raise an exception, like an interrupt, a special condition that causes the processor to deviate from just executing instructions in order and jump and execute instructions somewhere else. So if the operating system can try to handle it, if you don't handle the exceptions in the code you write as a developer, then the operating system will either pop up a box saying this process has stopped, or you'll get the blue screen of death if it's an unresolvable error in the kernel. But you can add exception handlers, and a professional coder would, so you don't let your program crash. When a bad thing happens, you handle it inside the program. So if you in your debugger, you can view the SEH chain. This is the structured exception handler. And what happens is when there's an exception, it will call this code and call that code. It'll call this code and see if it handles the exception. The exception comes with a number, a code number identifying the type of exception. And if it isn't handled by this handler, it will try that one. If it's not handled by that handler, it will then give you a pop-up box or the blue screen of death or something. So that's the SEH chain, and we're going to exploit it in later projects. You can exploit it. If you can insert data into the SEH chain, then you can trigger an exception, and it will then execute the code you chose. It's a way to gain control of the processor. All right, so you need a debugger. Just like we use GDB on Linux, you need a debugger for Windows. There's something great and powerful called Soft Ice, but it's out of date and I've never used it. It's obsolete essentially. WinDebug is by far the most powerful one. It is the one used by Microsoft, written by Microsoft. All the experts use it. It is very hard to use. We'll use it a little bit later in at least my 126 class we use it. I don't think we're going to use it in this class. I don't think I have any kernel exploits in this class. It's not much fun to use, but it's very powerful. The main thing we do is use OllyDebug, is the classic one that exploit developers have always used, which is very popular and easy and has a great GUI, but it was old and abandoned, and they upgraded to version 2, but it wasn't much better. But the code base was purchased by Immunity, which then continued to develop it. So Immunity Debugger is basically the more modern version of OllyDebug. And it's easy to use and pretty, and it works very well. And this is the main debugger we're going to use in this course. Everybody loves it. There are other ones called x86 Debug and x64 Debug, which are open source, which have the same UI, because this is the standard UI. Olly had the UI that became the standard, as far as I know. There may have been something else before it, but everybody lays out the debugger the same way. So here's the basic structure of the Immunity Debugger. The fundamental problem, of course, is that it's complicated. There is far too much information being presented here, enough to be confusing and frustrating. So you have to focus on the important stuff. And the general rule is these things, I don't know if it does Python. I've only used it for Windows executables. I don't know if it's a Python debugger. I don't know if it can do any other languages. It's a good question. I think Ghidra can, the NSA one. Anyway, so here, the fundamental issue is the experts want to see the little details. Beginners want to see something easy, but the experts don't care anymore. So the fundamental rule of all these complicated interfaces is always look at the right and the bottom, because they take the easy stuff and they shove it out of the way because the experts don't care about it anymore. So when you're a beginner, you start at the right and the bottom. This is the most important thing. Is your program running or not? It's paused. So you're not going to get it to do anything. It's just sitting there. When you load a program, it loads it in memory and stops. It doesn't run the program until you run it with this run button. So that's the first thing that you hear to people. It tells you it's paused. And then you have these 4 panes. This is the assembly code that's going to be executed. Here's the address, here's the hexadecimal bytes of the instruction, and here's the mnemonic, semi-human readable version of the instruction. These are the instructions. These are the registers, the same stuff we paid a lot of attention to in GDB. You have EIP, the instruction pointer. You have ESP and EBP, which is the top and the bottom of the stack frame. And you have EAX and EBX and so on. These are the registers, which will be important to us. This is the stack. So you can see here ESP is ending in 5C and EBP ends in 88. So here's 5C. Here it counts forward 4 bytes at a time. These are a series of 32-bit words. This is a pointer to returning to somewhere in NTDIL. Here's some data like some zeros. Then here's another pointer. Here's a pointer to the structured exception handler, and so on. This is the contents of the stack. And over here is just a hex dump pane where you can dump any area of memory that you want to and examine it in raw hexadecimal or in ASCII. So you can use this to examine any memory region in detail. And all right, and down here is a message telling you what's going on right now. So the attached process has paused somewhere in NTDIL at a breakpoint, which is it had finished loading and now it's stopped before running. So that's the general layout of Immunity, and we're going to use it in today's demo after this. So let's look at the last Kahoot, which is 6C. All right. Yes, there we go. All right. Got to get my virtual machine going for the demo. All right. All right, let's see. I'll give it a few more seconds. That looks like I better. All right, maybe everybody's here now. All right. All right, where are the inputs and outputs of an object? Yeah, that's the interface descriptor language. And by the way, people saying like daylight savings time, what they're voting for is to make this time permanent, the time right now, the time when we have the light. So not the other one. They would just like to never go to the other one, or it gets dark so early. Anyway. Yeah. All right, 128-bit value. That's the UUID, which stands for Universal Unique Identifier, and which obeys the Microsoft rule that it is not universal. It's not universally unique. Like there's one for control panel that's the same on every Windows machine. So, you know, like I say, you can always tell a Microsoft object because the name is always the opposite of what it really is. Anyway. All right, what structure is used when you divide by 0? Yeah, the structured exception handler. That's an exception. So you go to the SEH to see if the developer wrote any code that will handle that exception. All right, what listens on port 135? All right, that's the RPC endpoint mapper that lists the various services that are available to connect to over the network. All right, and which one of these is 32 bits? That's the token that determines who owns a process, and therefore what privileges they have. All right, so which debugger can debug the kernel? WinDebug is, we must use that to debug the kernel. That's why you put up with it. But the easy ones like OllyDebug and Immunity, you use only for user land, and that's what we're going to do. All right. All right, good for TV, 3 times. On JC, I think that's probably the same JC as before, I hope. And that's a first time Lou won today. All right, good. So, I'm going to stop the video